Welcome to the AWG Knowledge Center. My name is Christopher Skak, and today's topic will be about the precompensation plugin for the AWG70K series. Wideband signals created from signal generators are often limited by the bandwidth of the instrument's frequency roll-off and the losses associated with the cables, connectors, and external devices. This means that the influence of the generator's hardware and the connecting components create losses on the signals that can distort the signals and impact the ability to test the device under test appropriately. So these system artifacts need to be de-embedded from the signals before sending them to the device under test. All digital to analog generators, such as AWGs, have a characteristic sin x over x roll-off that is caused by the sample and hold architecture used in the DAC-based systems. This sin x over x roll-off can be easily compensated for in order to achieve the true hardware bandwidth of the generators. As we can see in the slide, the effect of just compensation of the sin x over x roll-off, but there is still the hardware bandwidth that reduces the output of the signal down to 6 dB at 20 gigahertz. So even though the hardware bandwidth is specified at 13 to 15 gigahertz, it is possible to output signals up to the frequency max specification that is determined by the maximum sample rate of the instrument. So not only would you want to compensate for the sin x over x roll-off, but ideally you would want to compensate or flatten the response all the way out to the frequency max to enable you to do this full frequency response of the instrument. Also, during this flattening, you would like to maintain the phase relationship of the signal being generated. Considering the AWG has its own bandwidth and frequency response, you also need to consider the effects of the whole network that you want to send the signal through. All cables and connectors will have their own losses and reflections associated with them, not to mention if other devices such as filters, amplifiers, delay lines are in the signal path, they also need to be characterized so that they can be compensated for. So the first challenge is to characterize the test setup, which includes the generator, the connectors, the cables, and any external devices used. To create this pre-compensated waveform and effectively de-embed the system components, the signal path needs to be evaluated by measuring the amplitude and phase of the signal at the device under test to determine what the losses are, and then create a correction file and apply it to the test waveform, thus de-embedding these losses in the system, effectively creating the cleanest signal possible at the device under test. In order to characterize the system, a known stimulus signal, golden signal, is created as part of the precompensation process. This will be passed through the complete system, including the signal path network, which needs to be de-embedded. This wideband multitone signal is created and generated out of the AWG and fed through the signal path to an oscilloscope or real-time spectrum analyzer, which replaces the device under test in this case. The resulting signal is analyzed and the magnitude and phase characteristics of the system are obtained. An inverse filter is then created and saved as a correction file. For this compensation, having higher resolution DACs, such as the 10-bit DAC used in the AWG70K series, enables the ability to compensate for higher loss signals that may be part of the system being tested. It is also required that wide bandwidth, low noise oscilloscopes or real-time spectrum analyzers be used to capture these signals correctly without adding additional losses that would reduce effectiveness of the compensation process. The precompensation plugin for the AWG70K series, or Source Express, which is a PC platform that simulates the AWG, offers several types of compensation methods depending on the application and if the AWG is a dual or single channel instrument. With dual-channel AWGs, the user can select from RF, IF, IQ with modulator or direct IQ settings. Single-channel instruments only allow RF or IF compensation. But in the near future, you could also use single-channel instruments that are synchronized together to create multi-channel signals similar to having dual-channel instruments. The RF may be used as a high-frequency coefficients or for single output from the AWG to the device under test. RF in this case could also mean high-frequency NRZ type waveforms too. In the example shown, the signal is being output from the channel 1 of the AWG and input to the channel 1 of the connected oscilloscope through the system cable devices that will be used in the final testing. Here we can see the definitions of the menus available. The sample rate is basically just an indicator of what the sample rate is when you started this process. It is important, though, that the sample rate that you use during the compensation is the same sample rate used for your outputted signal. Precomp also allows you to compensate for the second Nyquist zone of the DAC sample rate if so desired. This is generally used if you are trying to use the image as the output signal, effectively upconverting the carrier to the frequency band of the second Nyquist zone. In most cases, an external high-pass filter would be used during the compensation process to remove the first Nyquist zone from the output signal. Generally, most people just use the Nyquist zone 1 for their compensation. Defining the start and stop frequency determines what tones will be generated to effectively compensate for the frequency band of interest. Frequency resolution will determine how fine the slices of analysis will be, and will use more memory the finer the slices are. Number of averages enables averaging the results to remove excessive noise from the calculations. Usually 3 to 5 averages is sufficient. Scope trigger allows you to enable an external trigger to help with the scope's capability to trigger on low signals correctly. This selection is only available once you have connected to the scope. Here we can see the setup for an IF type signal that would be used with an upconverter and mixer. The IF coefficients are for a single IF signal from the AWG to the device under test. For IF type coefficients, you can connect to either an oscilloscope or a real-time signal analyzer, since it's just a single channel capture. In the example shown, the IF signal is being output from channel 1 of the AWG through an external mixer that the customer would provide, that is mixed with, in this case, just a 1 GHz local oscillator, and input to channel 1 of the connected oscilloscope or RSA. Basically, the same definitions apply to the IF that also apply to the RF settings. The only exception is where you put in the sideband frequency. Local oscillator frequency selection have been added to enable the mixer selections. The IQ with modulator coefficients are individual I and Q signals from the AWG and modulated with a carrier frequency to provide a single RF signal to the device under test. The IQ with modulator selection is only available if the active generator has individual channels available for the I and Q signals. In the example shown, the I and Q signals are being output from the channel 1 and 2 of the AWG through an external modulator that is modulated with a 1 GHz carrier frequency and input to channel 1 of the connected oscilloscope. Again, most of the same settings are similar, except here we also have the specifics for the modulator itself, and the modulator would be an external device that the customer would provide. The direct IQ coefficients are individual IQ signals from the AWG and connected directly to the device under test without a modulator involved. For direct IQ coefficients, you must connect both channels to an oscilloscope to capture the waveform, since 2 channels are required, So in this case, an RSA cannot be used for this compensation. In this example, shown, the I and Q signals are being output from channel 1 and channel 2 of the AWG and input to channel 1 and channel 2 of the connected oscilloscope. Again, these configurations can change depending on what channels you want to use on the scope. And again, we have the trigger capability if you have low signals that you want to use an external trigger for. As you can see, the IQ Direct, you have the same options, except now we've added options for bandwidth and offset components required for the IQ characteristics. The instrument performing the acquisition of the signal should have a bandwidth higher than the band of interest. The measuring capturing instrument should not add any of its own artifacts or distort the signal, which would be characterized. Thus, a near ideal capturing instrument would be required. Tektronix wide bandwidth oscilloscopes suit these requirements. Scopes with sampling rates as high as 200 gigasamples, bandwidths up to 70 gigahertz, analog to digital converters are ideal suited for doing this type of compensation of the AWG signals. The scopes also provide the ability to capture large record lengths, which will give better frequency resolution for the analysis. The time domain flat top window is first applied on the signal once it's captured. Obtaining the magnitude response is then calculated by looking into the frequency bins of interest that you've defined when you set up your compensation criteria. Correlation is done to acquire the right time alignment of the signal. Correlation is also done between the acquired signal and the stimulus signal. As the acquired signal is captured with a different sampling rate than what is generated, the stimulus signal needs to be recreated with the sample rate of the acquired signal. So this is all done in the background so that you don't have to worry about it. From the real and imaginary parts of the FFT, the magnitude and phase response is obtained. Magnitude and the phase response at the exact bins of transmitted signals are examined for measuring the distortions. Phase response requires a time reference for the acquired signal, so before taking the FFT of the acquired signal, proper timing and alignment of the signal needs to be done. The time-aligned signal is then analyzed in the frequency domain by taking the FFT of the signal. The phase response is unwrapped and the phase distortions are obtained. The difference in the stimulus phase and the stimulus signal phase is compared and the difference is captured. This provides the phase distortion in the captured signal. Group delay distortions are derived from the phase information. The inverse frequency response is stored in a correction file. This correction file is similar to an S1P touchstone file and can be used as such if you're wanting to use it as a S parameter file. To apply the correction file, once you've done the compensation, the user just needs to right mouse click on the waveform in the waveform list that they want to apply it to, and then select the correction file that they've created. The specific waveform for the test can be created using any of the waveform generation tools available. So you can basically create your waveform using either on one of our waveform generation tools built into the AWG, or if you're using MATLAB, you could also create a waveform using MATLAB and then apply this correction to that file. If the waveform is NRZ type waveform, the user also has the option of turning off the sin x over x correction, thus reducing the filter effects caused by that correction, or applying a Gaussian filter to the file when the correction is applied. The impulse response is obtained by the frequency sampling method by taking the IFFT of the correction factor. This impulse response is convolved with a signal of interest to obtain precompensated de-embedded signal. It's also important the correction was done at the sample rate, as I mentioned before, so that the time and phase relationship is maintained. This may require changing the properties of the waveform sample rate attribute so that it matches the compensation file of the sample rate that you want to use. So if you create a waveform using MATLAB, you want to make sure that when you import that waveform to your AWG, you go into the properties of that waveform and make sure that the same sample rate is associated with the sample rate that you want to actually send that waveform out as. So here we can see an example of a signal before compensation and one after. This effectively shows how much signal can be improved by using the signal precompensation. The AWG70K series also has the ability to apply S parameters files to the output signal. These S parameter files can also be de-embedded to remove the loss associated with a specific device, such as an electrical to optical modulator. So this allows precompensation, including losses that can't be tested with just an oscilloscope. Many devices include S parameter files to allow this capability. If an S parameter file is not available, then a network analyzer could be used to create one. So the S parameter capability, this option allows the user to emulate the device characteristics from S parameter files over frequency range of interest. It also allows users to emulate cascading of devices without physically having the devices. So in many cases, you want to create a system, but you don't have all the equipment there to send the signal through to include the losses associated with that particular device. So you can use an S parameter to simulate that. Other instances, you may want to de-embed those particular devices out of the losses that are associated with the network. So this capability gives you the ability to either de-embed it or not de-embed it and use it as a simulation of what that particular device will do to the network of the system. This S parameter provides the magnitude and phase response of a set of frequency values of different combinations of the input-output of the device. The S parameter, each combination of the input-output defines different characteristics of the device. These magnitude and phase responses are used to create a filter using an IFFT. IFFT requires that all of the frequencies be equally spaced, and we need to have values from 0 Hertz to the Nyquist sampling rate divided by 2. If the S parameter file does not have this information on the 0 Hertz or does not have the values up to the Nyquist, a constant interpolation closest value is chosen. Many devices include S parameters, as I mentioned before, files to allow this capability. If an S parameter file is not available, then again, you could use a network analyzer, or in some cases people use TDR methods in order to create S parameter files. The S parameter selection can be found under the Modify Waveform selection when right-clicking on a waveform in the waveform list, but it is only viewable if the S parameter option has been licensed. So the conclusion here is that in order to create signals to test your devices under test correctly, in many cases it requires that you de-embed some of the losses associated with the actual generation equipment and also the cables and connectors and devices that are associated with the network through the where the signal will pass through. So this is a very effective tool that we provide in order to give you a simple way of doing these compensations without having to write MATLAB code on your own to do this. It's very important to be able to have this capability, and we've tried to provide the easiest method in order to give you this capability. So you can go to our Tektronix.com website and download the Precomp plugin, and you can use it in your AWG, or if you're using Source Express on a PC, you can also load it on your PC. It does require a license in order to run it, and you can get a 30-day trial license, a fully functional 30-day trial license from the website. Then you can test it, see if it works for you. If it does, then you can go in and purchase the actual license. So this concludes this presentation. I hope it's useful. We'll be here again to show you the next plugin that we have available. Thank you.